Hello everyone, welcome to this latest video on moments of area. Now what we're going to be looking at is the second moment of area, also called the area moment of inertia. And this is specifically for engineering statics, dealing with area, but it compares similarly to dynamics, which you usually see in the third semester calculus course when we're looking at mass. A comparison between statics and dynamics. For statics, the key is finding the area, which is just the integral under the area, which formally that's going to be the integral of our top function f of x minus our bottom function g of x. To find the statical, or the first moment of area, qy, that would be the integral x dA, which is just the integral of x times the quantity of the top function minus the bottom function. Whereas the first moment about our x, qx, that statical would be the integral of y dA. Converting everything to x values, that would be 1/2 the integral of the difference of the top function squared minus the bottom function squared. Comparing those to dynamics, instead of solving for area, what's being solved for is the mass. And the integral under the mass would just be the integral of rho, the density of our material, times the area under area. And therefore, the two first moments of mass would be my and mx, which similar to the statical for area, that'd be the integral of x times the area under the mass, and then mx would be the integral of y multiplied by the area under the mass. Therefore, in both cases, COA, or the center of area, also called the centroid, you're solving for x bar and y bar, where x bar is the statical along the y, divided by the area, and y bar is the statical along x divided by the area. Where the center of mass, x bar and y bar would be the first moment of mass, either my or mx, divided by the mass separately. Looking here, essentially the first moment of area, the statical, that's just the distribution of an object's area about some axis, where the first moment of mass is the distribution of an object's mass about an axis. What's interesting is, when you're looking at dynamics, if rho is not a function, but is instead a constant, essentially what happens is, every time we see dm, well, when we take the integral of dm, that if density is a constant, then we can pull that constant out, such that we have density multiplied by the integral of dA. And then for my and mx, where we see the integral of dm again, essentially if rho is a constant, we could pull that out. So my over m, or mx over m, essentially the density would cancel out, because we would have rho over rho, but that's only if the density is a constant. In other words, if we have a constant density for a material, then our moment of mass just becomes our moment of area calculations. If density is not a constant, but is instead a variable function that can change, then that's where our center of mass becomes more complicated. Now, if we go into the second moment of area, what we're looking at is three values of inertia, Iy, Ix, and then the polar inertia, J. For our formulas, what we want is Iy, that's the integral of x squared times dA, or x squared times the difference of our top function minus our bottom function, whereas Ix, that would be the integral of y squared dA, or 1/3 the integral of the top function cubed minus the bottom function cubed. And then the polar inertia J, that's the double integral, r squared dA, essentially x squared plus y squared dA, or more simply, taking Iy plus Ix. Therefore, our inertia can be quantized as Iy, Ix, and J. Getting into dynamics, Iy and Ix, the second moment of mass, that's essentially just x squared dm or y squared dm. And this is useful in the angular torque equation, torque equaling moment of inertia, times angular acceleration. Essentially, that's similar to the inertia for mass. Now, second moment of area, also called the area moment of inertia, that's an object's resistance to bending along an axis, like IY or IX, or its resistance to torsion, say along the z-axis. That's what our polar inertia gives us. How hard is it to bend an axis along some axis, x and y, or to twist it along the z-axis? The second moment of mass, which is called the mass moment of inertia, that's just an object's resistance to rotational change about an axis. Normally, this type of inertia, moment of mass, moment of inertia, that shows up in physics as well as calculus. For area moment of inertia, that shows up for statics or sometimes kinematics in physics. Now, continuing on into our statics course, which is just area moment of inertia, or the second moment of mass, the second moment of area. What we're looking at is the higher of a value we calculate for IY and IX, that essentially tells us that it is much harder to bend that area along that given axis. The higher value we have for our polar moment of inertia J, the more resistant the area is to torsion or twisting, sort of like trying to turn a wheel. How hard would it be to cause that area to twist sort of in a spiral motion? Altogether, the higher the area moment of inertia, the stiffer the material is with respect to that axis. And you'll see this concept in a future course if you continue on in engineering, usually called strength of materials. This shows up in the calculation called Euler's critical load, where essentially if we had a beam and we had a load force on top of that beam, if that beam was straight vertical long ways or long ways horizontal, how well would it be able to stand against that load force without essentially bending or twisting or getting into torsion? And if we try to hit the beam long ways, vertical force on a vertical beam, very stable. If we were to take a vertical force on a horizontal beam and hit the center, it'd be less able to hold that load and more likely to bend. Now, getting into the correct units for our statics moments of area. Area, that's always going to be our unit of length squared, whether that's meters, feet, centimeters, inches, kilometers, yards, anything like that. The statical, that is the first moment of area, that is QY and QX. Those values are always going to be length cubed. The centroid, where we take our statical divided by our area, length cubed divided by length squared, gives us a centroid in units of length. That's how we're able to plug that along our x and y axis. Inertia, however, both IY, IX, and our polar inertia J, they are in units of length to the fourth power. So when you write your values, also include the correct lengths as well. For our first example, let's say we take the function, our top function is the function x, and our bottom function is x minus 2. So essentially two parallel functions. And let's look at the inertia values from the values of 2 to 4. Essentially, our area is not centered about our axis, but is a little bit further away from our axes that we're trying to measure how well it could bend or twist along those axes. So we're measuring the inertia further from the axis as opposed to being evenly distributed along those axes. Well, IY from 2 to 4, that would just be x squared times the quantity of our top function minus the bottom function, which it would take x minus the quantity of x minus 2. That is going to simplify to 2, and then we just have 2 times x squared. Take the integral of that, That would be 2/3 x to the third from our values of 2 to 4. That gives us 2/3 times the quantity 64 minus 8, or 112 divided by 3 as a fraction, which is approximately 37.3 meters to the fourth power. Now, let's look at Ix. That would be 1/3 times the integral from 2 to 4 of our top function cubed minus our bottom function cubed. Properly distributing everything, what we'll eventually get is x cubed minus the quantity of x cubed minus 6x squared plus 12x minus 8. Distributing that minus sign across the things in parentheses, our x cubes are going to cancel and we're going to be left with positive 6x squared minus 12x plus 8. Taking the integral, that gets us 1/3 times the quantity 2x cubed minus 6x squared plus 8x from the values of x 2 to 4. That comes out to equal 56 divided by 3, which is approximately 18.7 meters to the fourth power. And then finding our polar inertia J, just take your values of Iy plus Ix, which comes out to be exactly 56 meters to the fourth power. So to represent our entire inertias, that would be Iy, Ix, and J, parenthesis 112 over 3, comma 56 over 3, comma 56, and then you could also include the units meters to the fourth, parenthesis. Now, this is solving for the inertia of our two functions, but we're looking at a segment of area that's not evenly distributed about any given axis. Let's instead look at the inertia values of those same two functions, but now from x equaling from x equaling -1 to 1. So effectively, our area is evenly distributed about the axes that we're going to be measuring resistance of those area from bending along those axes. So solving for Iy, well, we're still going to end up with taking the integral of 2x squared, but now from -1 to 1. What that actually gives us is Iy equaling 4/3, or 1.3 meters to the fourth power. Already our resistance to bending along that axis is substantially lower, and that's the trend we're going to see. If we're trying to measure inertia for an area where the area is evenly distributed along an axis, it's much easier to bend that area along that axis, or we'll get a lower calculated inertia value. Now Ix, well, we're still going to have the same two functions, so that's still going to eventually give us 1/3 times the quantity 2x cubed minus 6x squared plus 8x, but now ranging from -1 to 1, that's going to equal 20 over 3, 20/3, or approximately 6.7 meters to the fourth power. Again, now that our area is evenly distributed along that axis, to bend the area along that axis is going to result in a substantially lower inertia. It's going to have a lower resistance to bending along that axis. And naturally, if Iy and Ix are much lower, because our area is evenly distributed along the y-axis and also distributed evenly along the x-axis, our polar inertia J is going to be much lower as well. Where we get that, J equaling Iy plus Ix, 4/3 plus 20/3 equals 8 meters to the fourth. Therefore, our new inertia for this area from x equaling -1 to 1, that would be 4/3, 20/3, and 8 meters to the fourth power. And what that's meant to show is, as we take our inertia equations through statics, how our area is distributed along a given axis will affect the magnitude of our inertia values. And the more evenly distributed the area is along the y-axis, the lower it will have a resistance to bending along that axis. And the more evenly distributed that area is along both the x and y, that results in a lower polar moment of inertia. In any case, that would be the conclusion of this lesson into our second moment of area. As always, likes and subscribes and comments, not necessary, but appreciated. And we'll see where this channel will go in the coming months and years. In any case, glad to have you all for this video. And as always, peace.